Welcome to part 2 of the chapter 24 homework preview. I'm going to do problems 42, 46, 54 and 60. So let's start with 42. The setup for 42 is that we have a charge in the center of a sphere. So the charge in the center is charge Q. Indication is it is positive. And there's a charge minus 2q, so twice as much, spread out over the surface of this outer sphere. This sphere, this shell, right, is hollow on the inside except the charge in this charge in the middle, and it has negligible thickness. So those walls, if you imagine having an actual shell, you can't have zero thickness walls, but for all practical purposes, in this case, we're going to pretend that the walls of this shell have zero thickness, so that the charge, the minus 2q, is spread out over this surface in a sort of infinitely thin spherical sheet, a shell, right? So the symmetry of this, right, this is an actual application of Gauss's law. We are trying to find the electric field inside and outside of this sphere. So this sphere has some radius, and I'm just checking. We're told it has a radius capital R from the center, and we're trying to find the electric field both at a point inside as well as a point outside. So it should be immediately obvious, right, that the symmetry of this is spherical, right? It's a point in the sphere, so no matter what direction I'm looking at this from, it's going to look the same. So that tells you right away that the electric field has to be radially in or out. Right? It can't be at some funny angles, it can't be sort of coming out like this, because that would violate the symmetry of the spherical setup. I went through this in some detail in my videos where I explained some applications of Gauss's law. So let's figure out what the electric field strength is. So let's start with a point inside the sphere. Let me take this point here. So I want to find the electric field strength at this point here. This is an arbitrary point as long as it's inside the outer shell. I'm just going to say it's a distance small r from the center. Because the setup is spherical, you're going to pick a Gaussian surface that matches the symmetry. There's a sphere around the same center. So in this case, it will look something like this. A poorly drawn sphere, but you can hopefully, we can see what I mean here. And again, you have to think in 3D, right? It's not a circle inside a circle. It's a sphere that comes out like this. And the same thing about this sphere here. It's like I've cut it open, but really it's a 3D object, and there's no way to actually look inside it. So we're going to figure out what the electric field is. It's going to be radial, right? So that means that at any one point, the electric field and the direction of the surface, like the orientation of the surface, they're parallel to each other. If I draw a little flag here, right, this is my little flag, it shows me the direction of this little surface chunk here. This is going to be parallel to the electric field, which is necessarily radial. Now, I'm not going to quite show you the direction yet. You can probably guess. The inner charge is positive, the outer one is negative, and electric field tends to go from positive to negative. So, well, whatever the value is, let's just put it in, it's going to be outwards, right? Because it's a positive, it starts at a positive charge, ends at a negative, it has to be radial. That's the only way the electric field can be. This is a spherical setup. If there was just the inside charge and not the outside charge, the answer would be immediately obvious, right? It would essentially be like application of Gauss's law would give us back Coulomb's law. But let's apply Gauss's law in this case. So because the flag, right, the direction of the flag, the direction of the little surface element, that's what I mean when I say the flag. It's kind of a nice way, I think, to visualize it. Is parallel to this, I get that the flux that the flux of this tiny area element dA, right? I imagine this tiny thing to be infinitesimally small. The flux through this is going to be equal to, well, it's E dot dA, but because they're in the same direction, they're parallel to each other, that is just the strength of the E field times the area itself. And then to work out a total flux, across this whole Gaussian surface that we picked, that sphere of radius small r, well, I just integrate this, but this is constant, right? Electric field is constant by symmetry. It's always the same distance from the center. It looks the same from all directions. So this comes out, and I just multiply by the sum of all the areas added up, right? This is what this means. Where I guess you call the surface S, and I mean, of course, this sphere, right? This imagined sphere of radius small r, that's our surface. So this thing is just the surface area of S. What's the surface area of a sphere? You can figure it out. But then Gauss's law says that the total flux is equal to the charge inside divided by epsilon naught, right? What's the charge inside? Inside what? Inside our Gaussian surface. The point charge in the middle is definitely inside. The shell around it is not inside, right? If I imagine this thing being this green ball, right? And this were like some kind of metal sphere. None of the metal of the sphere is inside the green ball here. So the outer shell just doesn't count, but the charge inside is just Q. So having worked it out, you can figure out what the electric field strength is. And what you notice, because the shell is the outside, it doesn't actually matter for the electric field strength inside here. Right? Remember also, another thing we've learned in the past is that if there were just the empty shell, there would be no electric field inside. And then you put a point charge there, so the combined field here is just the sum of the field due to this one, which is 0, plus the electric field due to the point charge, which is essentially given by Coulomb's law. So you could actually solve this just using the superposition of two electric field contributions, namely the electric field contribution due to the sphere plus the electric field contribution due to the point, and work it out that way. That would also work. Now, this is if you're on the inside. If you're on the outside, right? If you have, if you're on the outside here, say, we just call this R. Sorry, this it should be Academy R. R in, R out. Right, just give them two different names. Then, working out the flux through this bigger surface we now imagine, right? Again, you want to imagine symmetry, so again, our Gaussian surface is itself a sphere, except this time it's bigger than the sphere that it carries the minus q charge. So that implies that while the flux calculation looks the same, except the area is going to be different because it's a bigger sphere, the charge inside is now going to include the total charge on this. So for the Q, if R is smaller r, right, if we are interested in the point on the inside, but it's equal to Q minus 2q if r is greater than r, because that is the total charge inside. There's one, if q were 1 coulomb, that'd be 1 coulomb of positive charge in the middle and minus 2 coulombs on the sphere, so it'd actually be a negative value. And you can imagine the electric field outside could be pointing inwards. Another sort of sanity check you can do is that if you imagine you went really far away from this whole setup, like you zoom out, this whole setup disappears into the distance, then all you see is a point charge. Right? No matter what shape this is, as long as it's not infinitely big, which it isn't, all you see is a point charge if you're really far away. So the electric field really far away should be the same as the point charge, as the electric field due to a point charge that has the total net charge of the setup. In this case, that's minus q, so it's a negative net charge. So from far away, you expect the field to match that of a minus q point charge. It's a sanity check you can do. That gives enough information to solve this one. Let's move on to the next question. Here's number 46. The setup for this one is that you have an infinite slab. So it's kind of like an infinite sheet, except it has a thickness now. It's not all the charges in a single sort of two-dimensional surface. It's spread out over this sort of solid block, if you like. I try to draw it here. Of course, I can't draw it infinitely big, but you could imagine it keeps going in the sort of horizontal direction, but it has a given thickness. And the thickness is given by 2z0. The 2 is probably just to sort of allow us to say, look, we're going to take our z equals 0, the z-axis being vertical here, our z0 in the middle, and then we go, z0 above and z0 below. And that is the thickness of it. And then what we are told is that it has a uniform volume charge density. Right, so let me write this down. Volume charge density rho, so the Greek letter rho, kind of an R sound, it looks like a curly P. That's to say, what is this? This is how many coulombs are there per cubic meter. Right? So if I imagine I'm going to cut a cube out of this, again, it's hard to draw this in 3D, but I could imagine I have sort of maybe a cube like this, and the cube is 1 cubic meter, then, well, the rho would be the amount of charge in 1 cubic meter. If I have a cubic centimeter, well, there are 1,000,000 cubic centimeters in a cubic meter, so it would be 1,000,000th of the numerical value of rho. Alright, this is kind of how much charge do I have there per volume. It's a little bit like the mass density. Like a mass density per volume, you say, water has 1,000 kilograms per meter cubed, or 1 kilogram per liter. Right, that would be the mass density. Same thing here, how much charge is there in one volume. That is what we know. So I try to draw this a second time down here, sort of from the side, right? So you can imagine like the sort of x-axis this way, y-axis goes towards the back, and then z-axis is vertical. You can imagine drawing x or y here, right? It looks the same, and z upwards. So you can look at this kind of cross section of the slab. It keeps going forever in the sideways direction here. I want to find, for this example, the electric field strength inside the slab and outside the slab. Now, the setup here is essentially the same. You can see what the symmetry of this setup is, right? It's the same as a sheet. I can move it like this way, I can move it this way, I can rotate it. So I'm going to pick a Gaussian surface that matches those. And the way I'm doing this is exactly the same as I did for just the infinite flat sheet, which is an example you've hopefully worked through before tackling this problem. So suppose I'm going to use diagram down here. Suppose I want to figure out what is the electric field, say at this point out here. I'm going to start with a point that's above the sheet. I could imagine it is some height h from the xy plane. Therefore x minus z naught above this the top surface of my slab. So what type of Gaussian surface am I going to pick? Well, I'm going to pick a Gaussian surface that is going to end up having the same electric field everywhere, and by the symmetry of this, the electric field is going to be the same everywhere that is the same height above the slab. Right? Because I could imagine shifting the slab sort of left-right. It doesn't change the way it looks at all. So that means the electric field better doesn't change the way it looks just by moving it left-right. So the electric field has to be the same everywhere as long as I'm the same height. And then I'm going to make it symmetric. I'm going to go down the same distance like this. So this is kind of my my Gaussian surface. If I try to draw it in 3D, it's hard. Let's say I'm going to draw it like this. I'm going to use a rectangle, and then this goes sort of down like this. I'm going to pick vertical walls. Then it cuts into the slab, keeps going, and somewhere deep down below, this is really hard to sort of visualize here, it's going to come out. So it's symmetric about the center, the sort of center cut of the slab. I think it's easier to see down here, but you can't see the top or bottom surface on this drawing. You would imagine it sort of goes backwards like this, I guess. This is bad 3D drawing, like this is technically wrong, because I've got it from a front view, but this is kind of how you could imagine it. Maybe like this a little bit. So by the symmetry, I know that the electric field has to be pointing vertically, right? It can't be at an angle. If it were at an angle, say if the electric field was sort of pointing diagonally like this, right? Then I could just imagine I rotate my whole slab. That doesn't change the way the slab looks, because it's just an infinitely large sheet with a certain thickness. But that would rotate the electric field, so the electric field would not match the symmetry of the charge distribution. So the electric field has to be vertical. And it has to be a vertical electric field. Now, if the slab is positive, well, we know it's going to come out of positive charges. The electric field up here is going to definitely gonna go up. What does that imply? That implies there is no flux to the sides, right? We understand that by now. There's no flux to the sides. Because the field lines, they just sort of graze along the surface here. They don't cut it. They're in the same direction as the surface, or in other words, they're 90 degrees to the flagpole. So there's no flux on the sides. So all the flux is a result of this sort of thing. Right, of the field lines coming out the top and coming out the bottom. So if we choose, right, we have a choice here, if we choose the top to be an area A, and it doesn't matter whether you pick a rectangle or anything else, circle, a pentagon, who cares, some freeform shape, area A up here, area A down here on the bottom as well. And by the symmetry, because the slab looks the same if you look at it from above or below, you're just going to get twice the flux due to one surface. Right? So the flux is going to be the electric field strength here, flux through top and bottom is going to be A times the field strength. So let me write out, but because E is constant, I can
essentially just take the flux is the total area dotted with the E field. The angle is 0 between the flux sticking out the top and the field lines. So this is just the area times the electric field strength, the magnitude of the electric field, and that's each. So you've got 2 of those. That is your flux, right, through this imagined surface here. So what is the charge inside it? Well, the charge is contained in the volume of the slab. Okay, so let's find the charge inside. Charge inside is the volume inside multiplied by how much charge is there per volume. Charge, so it's hard to read, charge per volume. So this thing is the thing we called rho. This thing is the thing we have to figure out. Now, I can sort of draw it here. You've got to imagine that this is this sort of cube in here. I'm mixing 2D with 3D drawings. It's terrible practice, but hopefully you get the idea, right? If I sort of imagine it's like a cookie cutter, right? And you sort of cut out of your slab, if this is your dough, the flat chunk of dough, you sort of cut out this, in this case, rectangular cookie, right? What is the volume of that cookie that you've cut out with your Gaussian surface? Maybe that picture makes sense to you. Well, the area of this top piece here is A, the height is 2z0, the top area A, 2z0, the volume inside is going to be, let's write out, height times the area, which is A, right? So this area here, same as this area here. So now you can apply Gauss's law. I'm not going to write this down for you. You can do this by now, right? Charge inside over epsilon naught. That's the right hand side of Gauss's law. Total flux, like you've worked it out here. That's the left hand side of Gauss's law. That allows you to set those equal. That will allow you to find the electric field strength if you're at a point above or below the slab. Same thing, right? We don't even know which side is above. There's no difference. What about if you're inside the slab? I'm going to draw this picture again. I'm going to try to draw it a bit bigger. So here's my slab, right? And I guess I'm going to have a sort of axis here, just to have some kind of reference point. This is the middle. Now I want to know the electric field here, right? This is Z naught. And in this case, what you'll find, but in the case where we are above the slab, you'll notice that your final answer won't actually depend on how high up you are. The logic being very similar to just the infinite sheet. In this case here, the situation is a little bit different, right? Because the symmetry is the same. So if I draw my surface, right, I want it to be symmetrical above and below to match the flipping symmetry of my slab. And I guess I'm going to try to do the same thing again. This whole Gaussian surface is now on the inside of the slab, right? So if you're looking at it from above, you can't see any part of the surface, entirely on the inside. And if you imagine it extends the distance z above, I guess this is down to this one here, above and below, right? You get the idea. It's the height, top area here, A, the bottom area there, each a distance z from that center line. So now, the left-hand side of Gauss's law is the same, right? The flux, again, just by the symmetry, we know that even inside the slab, the field lines, they have to be vertical. Right? All the field lines, they're going to be vertical.
and you probably guess that the field lines up here are going to go up, the field lines down here are going to go down, just from the reasoning that if I'm above, right here, right, there's more charge beneath me than above me. Okay, so the same logic applies for calculating the flux, right? So flux, same as before. So the left-hand side of Gauss's law doesn't really change at all, whether you're inside or outside. But what is the charge inside? Well, before, the thickness of our cookie that we are cutting out of the slab was just the whole thickness of the slab. But now, the whole thickness of the slab isn't inside my Gaussian surface here, my Gaussian tower. The volume inside it, right, is just A times the height. The height is not 2 times Z0, the height is just, well, 2 times Z. So it's again the volume inside times rho, the charge per volume, but the volume is now just the volume of the actual Gaussian, of the inside of the Gaussian surface, not the volume of the whole slab cookie. The volume here is going to be just the base area, or top area, times the height given in terms of Z. So in this case, when you're inside, the field strength does depend on how far from the center you are. The higher up you go, you're going to find the bigger your Gaussian volume, the more charge on the inside, the stronger the field. So a more accurate depiction of this is not this, but it's more something like this, where more field lines start further up, right? Because they're more, if I imagine this slab being made out of lots of tiny charges, like lots and lots of protons, you can imagine that with some protons here that create their own new field lines, and then more field lines there. So the field actually gets stronger as you get closer to the edges. But once you're at the edge, it's just going to keep going. Right? It's just going to keep going without any new lines being created. It's just a constant electric field. So outside it'll just look like this. Those lines keep going and no new lines are starting. New lines are only starting on the inside because there are positive charges there. Okay. I think that completes the question. There is, well, it's asking us to draw it from z equals 0 to z equals 3z0, so 3 times this height above. And I think you told you how to do this. You figure out the details to actually set the left-hand side of Gauss's law equal to the right-hand side of Gauss's law, to actually work out what the exact expressions for those electric fields are. And that completes number 46. There are 2 questions left, number 54 and 60, but since this video is already about half an hour long, I'm going to stop it here and answer the last 2 questions, or help you set up the last 2 questions in part 3 of this homework preview. So I'll see you there.